Vanakkam. Welcome to this video on biomechanics. In this week, we get started with a new topic, which is practical applications. An example is how to measure individual segment kinematics in the human body. So, in this video, we will be looking at measurement of orientation in 3D space, devices that are available to measure orientation, and how to measure, record and compare the information from these, and what kind of measurement techniques are suitable for what kind of situations, experimental situations, and how to parameterize the rotation. Okay. So, when we measure kinematics, we are generally interested in, when you say generally kinematics, you are speaking about linear kinematics, that is displacements, velocity, acceleration, that is linear displacement, linear velocity, linear acceleration. Then in angular kinematics, you are interested in angular displacement, angular velocity, angular acceleration. Okay. That is, notation for these are S, V and A, is it not? Vectors S, V, A. Angular displacements are theta, omega, alpha. Remember, from our knowledge of high school physics and basic mechanics, I know that angular displacement is generally noted as theta, angular velocity is omega, angular acceleration is alpha, and in general linear displacement is S, linear velocity is V and linear acceleration is A, vectors. These are also vectors, by the way. The angular kinematics, those are also vectors. Now, in this course and in this video, we restrict our attention to angular kinematics and not linear kinematics. Why, we will see in just a little bit, because our interest in this case and as part of this course is to measure the joint angles or relative body positions, joint angles between joints, that is angle between two bones or rigid bodies is what we are interested in. So, we are mostly interested in angular kinematics in this course, and so we will be discussing that, we will be focusing a lot more on that when compared with. So, for example, when this person is lifting from, say, from this point to that point, so what is happening is essentially a linear displacement for most practical purposes, but the body itself might undergo changes that that might be in angular domain. Actually, how this changes in joint angle get converted to the linear space is a question, is an advanced topic that perhaps we will not be in a position to address in this course. Okay, it's something for you to think about. How joint rotations, I will leave this as an exercise, if possible you can try this, how rotations that happen about individual joints get converted to linear motion in the Cartesian space, that in the real world. How is that happening? Think about that. We will not discuss that as part of the course. Okay. For example, we are interested in rotations about various axes. For example, here we have a 3D coordinate system that is rotating. Right. We are interested in these joint displacements, these angular displacements, velocities and accelerations and so on and so forth. Right. Take the case of the human hand and fingers. As an example, I keep giving the human hand and fingers because it's a very dexterous system, but that is not the only reason. Also because I work extensively in the field of hand finger mechanics. So this is my bread butter water, this is what I do for a living. So obviously the examples that I will give will come from this space, but that is not the only reason. The reason is also that it is a system that is having a large number of degrees of freedom, that many examples can be given just with this one single system. That is the other reason. Here what is shown is the movement in a proximal interphalangeal joint, right. Some angular excursion that is happening at the pip joint, proximal interphalangeal joint. Note that these joints are modeled as hinges. They have only 1 degree of freedom, and so the movement is going to be restricted to that. Okay. And the amount of excursion that happen are also restricted by the anatomy and the muscles that are powering this. So the range of motion is also defined by that. Okay. Now we will spend some time discussing how we can measure orientation in 3D space. So we are interested in measuring orientation of a body, of a rigid body in 3D. What are the various ways in which you can do it? Which method is good, which method is better, which method is best? Actually, there is no single method that comes across as best in all the situations. So your choice of the method of measurement depends a lot on the specific situation or the application and how much money you can afford to spend. There are many things that come into the picture. One gold standard method of measuring joint angles or orientation is by using optical trackers. Okay. Before we get started with our discussion on optical trackers, I thought I will spend a few minutes discussing how you can measure body orientation using a regular web camera, because these kind of things, these kind of videos or posts you will see on social media, where people say that they were able to track hand finger motion or some body part motion using a web camera and a high quality algorithm. How are they able to do it? Well, so what they do is they use a regular web camera and they will use some standard markers. For example, they might put up a small dot, say 1 centimeter in diameter, something like that, white in color, and they will train a network to track this dot that is placed on the body part. They will have a high quality processing system, and so they will have an algorithm that uses, because the computational techniques to process this kind of information, to process video, are well developed, and the hardware that is available to process video are now well developed. They will have a high quality algorithm that is running in a high quality hardware system that will track this particular marker, so to speak. This marker is not a real marker. They will just place a small, for example, a 1 centimeter circular paper, a sheet of paper that is just put on the person's body part of interest using, say, double sided tape or glue or something like that, and that's then tracked using this algorithm. And usually these tracking systems are almost real time. So that means that they must be of really high quality, they must be very deep, they must have done quite a bit of analysis to arrive at this. So these kind of methods are now becoming more and more popular. Also there are these standard codes such as this deep lab cut, for example, that are used in estimating the pose from regular video. Remember, these kind of techniques rely more on software, rely more on code and hardware to run this code. So, the particular data capturing system itself might not be an expensive system. So, there are these kind of techniques that are coming up. However, in biomechanics, we are interested in not just getting a general sense of the posture. We are also interested in getting this data at a relatively high level of accuracy. So, we will focus on the standard research based techniques in the next few minutes, but I just wanted to introduce that there are these kind of webcam based techniques that are becoming available. Those of you who are interested, please explore this using just Google is your friend, just check deep lab cuts, what are the methods that are available to track posture using webcam. There are techniques that are available. Of course, that does expect you to be good as a coder. You need to be good with Python, for example. So, there are some expectations, but these are possible. These are now becoming possible. This was not possible when I was a student. This was not possible 10 years ago. Okay, this is now possible. There are a lot of these techniques that are now being developed, now becoming possible. You will have to edit the code according to your needs. So, that requires you to have not just coding capability, but also the ability to read good code and debug it according to your needs. So, that is a special skill. We will not continue that discussion further. We will continue our discussion on optical trackers. So, optical trackers, these are systems that use cameras to track posture of specific body parts or rigid bodies. These come in two flavors, either passive marker system or the regular camera based measurement system or active marker system. What is the difference? Well, the difference is that passive markers, the system is passive, active marker, the system is active. Well, you will have to define a little bit more than that, right? So, in the passive marker system, light is incident upon the markers that are placed on the body parts. The markers themselves just reflect the light that is incident on them. So, something to keep in mind that these are passive reflexive markers, reflexive or reflective, however you say it, whichever is the correct English word or technical word, check that. These are passive reflexive markers. So, that means that they do not have energy consumption by themselves. So, these markers are placed on specific body segments and light is incident on them, and these markers reflect the light that is incident on them. The cameras capture the reflected light, and then there is a calibration routine and a calibration method, and then a rigid body model of the measured body part is then being generated, which then is used to reflect these movements, hopefully in real time or at least for analysis. There are advantages and disadvantages to this system, which I will discuss in just 1 minute. Active marker systems are those in which the markers generate light at a given wavelength. This may be, by the way, in both these systems, the light may be regular visible light or IR light. Okay. So, active marker systems generate light at a given wavelength. So, each of the marker has a specific signature wavelength. So, if you tell the software, the managing software that is going to collect this data, where you are placing a given marker, the marker has a code number and that code number is placed, say for example, in the upper arm, and so the software is expecting light of a given wavelength from that marker, and whenever light of that wavelength is received, it knows that, it is coming from the upper arm. Another marker that is placed in the forearm, for example, will send this light at a different wavelength, and the system knows what is that wavelength too, and likewise for all these body parts. So, it knows based on what is the wavelength of the light that is measured, it knows from where it is coming, and so generation of this model is a relatively simple process. Not just that, sometimes what happens, let us say that I have a set of passive reflexive markers that are placed on my two arms, both these arms, and I am doing that, where you are watching me, where the camera that is measuring this movement is placed, where this visible light camera that is measuring our recording is placed at around the same place, and I am doing that, for example. Now, what will happen is that the markers that are the passive reflexive markers will cross over each other, right. For example, when I am doing that kind of a movement, there will be crossing over of these passive reflexive markers. Sometimes some of the markers will not be visible, so there might be tracking problems. Nowadays, software is available to automatically track the markers. Sometimes, nowadays, relatively rarely. In the good old days, 15 years ago, tracking this was a manual process, involved quite a bit of manual process. Now, more and more the softwares are becoming more and more smart, that they are able to do this tracking in a much better way, that the amount of manual intervention that is required is minimized, but it still is involving some amount of manual intervention. For example, when I do this, it is not clear which marker is, because the marker on the palm of the left hand and the marker on the palm of the right hand will cross over, and you do not know which palm is going where. There will be a little bit of a confusion. Usually this should not be there, but it could happen. So, there will be tracking. So, there will be tracking problem. So, the disadvantage of the passive reflexive marker system is that there may be tracking errors or tracking problem, or there might be a need for manual tracking in the passive reflexive marker system. If I use the active marker system, this problem will not be there. Why? Because the marker on the right hand and on the left hand will use different wavelengths. So, when I move, there is no confusion to the camera which hand is moving in which direction, because these lights have different wavelengths, or this light, or these two markers send out light at two different wavelengths. So, there is no confusion, and so tracking is relatively easier, extremely easy. So, there is no need for manual intervention. But is it that this system has no disadvantage? There is the disadvantage that active marker systems are active, that is, they require energy. If you have to generate light and transmit it, you will need to spend some energy that has to come from a battery. It can have a central battery from which all these markers are powered. That means that central battery will have to be connected to all the markers via a cable. Whenever a cable is involved, it is possible that cable might restrict movement. There are many constraints that come into this. Or the other idea could be that I can have individual markers that come with their own battery. In this case, there will be no cables, but the disadvantage is that each of the marker will be bulky, that it cannot be put on small parts of the body such as fingers. There are many challenges. So, challenges are there both for passive reflexive markers and for active markers. You will have to make the choice as to which one do you want. In general, optical tracking is considered gold standard when it comes to measuring kinematics. There is no second thoughts about that. There is no second, there are no challenges, there are no questions about that. Nowadays, technology is available to provide this feedback in real time also. So, there is quite a bit of advancement in this field. In general, optical tracking systems are considered the gold standard, and they are also somewhat expensive. There are some systems, for example, OptiTrack type of systems that are relatively inexpensive, but they have their own limitations as well. So, you cannot have the cake and eat it too, but there are now relatively inexpensive systems, or what are called as animation grade kinematics measurement system. I do not want to endorse or suggest names of companies. There are some animation grade kinematic measurement systems that are available in the market. Remember, these are animation grade. That means that they are not exactly research grade, but they can be used in research with a little bit of modification, with a little bit of challenge. They can be used to measure data for research also. Okay. So much about optical tracking. If you are interested in hand kinematics, like I am interested, mostly I am interested in hand kinematics more than whole body kinematics and rest of the body kinematics. I am interested in hand kinematics. If you are interested in hand kinematics, one option is using flex sensor based data glove, or some sort of data glove that uses resistive bend technology. There are some standard companies that are available that generate this, that manufacture these kind of gloves for hand and finger kinematics. The advantage is that there is no worry of line of sight. So, optical tracking systems also have this problem that at all times during the measurement, each of the tracker, each of the marker must be seen by the camera. So, there is a need for the camera and the marker to have line of sight. There should be no occlusion or obstruction between them. So, that problem is not there when you are using a glove to measure kinematics of the hand and fingers. So, this we get rid of this line of sight problem. Let us briefly discuss this data glove technology. What this does is it uses resistive bend sensors. The idea is that depending on the bend, amount of bend in the sensor, the resistance of that sensor will change. So, the output voltage will change accordingly. It turns out that over a relatively large range, the relationship between the amount of bend and the output voltage is linear, and it is possible to calibrate this. The challenge is calibration. You need to have this calibrated for each hand that you are using. You cannot assume one calibration or calibration used for one person to be true for another person. Usually it won't work. So, that means that each hand requires its own calibration. It might appear as if calibration works, but sometimes only when you perform relatively complicated maneuvers such as that one, where the tip of the little finger and the tip of the thumb touch each other. Right? Those are kinematic maneuvers that involve this palm arch. Right? These kind of maneuvers usually cannot be easily captured by this kind of system. There are many challenges with this. And you need to have them properly calibrated. Not just that, the accuracy of these systems are relatively limited. So, the accuracy is usually, you get what you pay for. There are systems that come for even few thousands of dollars. The accuracy is not that great. So, it really depends on whether you are interested in studying the mechanics at a detail level, where you are caring about the accuracies, where you are caring about 1 degree here and there. Or let us say that you do not care that much about that, but rather you are worried about general changes in patterns of movements, such as coordination patterns, such as learning. Those are more like you are interested in how the control or coordination pattern changes over a period of time or over a task, for example. In those kind of things, maybe you are not looking at that kind of accuracy. Again, I am not saying this is good or bad, I am just saying that these are available. Okay. So, there are some challenges with this. These are relatively inexpensive systems. The advantage is that line of sight problem is not there. Another advantage is that they are inexpensive. The disadvantage is that you compromise on accuracy, and they need calibration for each hand. So, that is other. The other idea is to use electromagnetic tracking systems. Those that use electromagnetic trackers, the idea is that there will be one transmitter like the one that is shown here. This is our lab setup. This is a lab. This is the equipment that we use in our lab. This is exactly the arrangement that we use in our lab, the neuromechanics lab at IIT Madras. So, where we keep the transmitter at one point, it sends out a magnetic field. So, movement of a given tracker within that magnetic field, it turns out is relatively linear over a large range. So, I can measure these movements depending on the field, right, so that I am measuring. So, this can be calibrated relatively easily. The challenge is the advantage is that line of sight problem is not there. The challenge is that these are expensive. It is an expensive system. These are extraordinarily accurate. They are very, very accurate. They are expensive, but there is a bigger challenge that instrumenting these on small parts of the body like the hand can be very tedious. And also most of these sensors are delicate. They need to be handled like babies. So, unless you are working with slow movements, these may not work well, because if they are very fast, there is a possibility that the cable might snap, which will essentially cause damage of this equipment. So, there are some challenges with this kind of equipment also. They are expensive, they are accurate, but they are expensive, and they are also fragile or very delicate. They need to be handled carefully, and preferably they must be used only for movements that are relatively smooth and not very fast, not high velocity. Sometimes when you are using fingers and when people are making that kind of very fast movements, it is likely that there might be a snapping of the cable and the coil that is used for the measurement. This permanently damages the sensor and is not covered by warranty. So, the manufacturer will not replace this for you. So, there are some challenges and difficulties with this kind of measurement system. Then something that we have developed in our lab, a variant that we have developed in our lab is an inertial motion unit based IMU, inertial motion unit based hand kinematic measurement system that we have developed in our lab. While we are discussing this, let us have a sense of the costs, right. So, if you are talking about optical sensors for whole body measurement, you are speaking anywhere between well, even if you go for the inexpensive animation grade like OptiTrack, you are easily, for whole body measurement, you are easily looking at around 20 lakh rupees. Data gloves, depending on the cost, anywhere between 5, but accuracy is less. Remember, for one pair of gloves, anywhere between 8 to 10 lakhs, I guess, about 8 to 10 lakhs. One has to really check for this. There are many ranges that are available. The best ones come at about 25 lakhs, right. The electromagnetic tracking system, the gold standard ones, easily going to set you off by about 30-35 lakhs for the 16 segments, for the 16 sensor system that is required for hand kinematic measurement. This one we have made in our lab. The manufacturing cost, not the cost at which we are selling this, the manufacturing cost comes to about 1.25 lakhs. So, but of course, you will say that, hey, but you are not going to get the accuracy that you are going to get with the optical system. Of course not. We are not saying that we will get that kind of accuracy, but we are getting some relatively good accuracy. So, our accuracy is sub 4 degree angular accuracy, and the cost that you are paying is like, you know, about $1,500, $1,250, $1,300. I think we have made quite a bit of progress with this, and we are continuing to improve this. We hope that we will be in a position to sell this whole system for less than well, when we sell or manufacture this whole system for less than $1,000 for one hand. We have published a couple of papers on how we made this. We are still continuing to improve this, and we are filing a patent on this technology in the next few months. We have a couple of papers on this topic. Please check my website. There are a couple of papers in IEEE Access. Both of these papers start with Shenoy. Okay, he is your teaching assistant for the current semester. The first offering, Prajwal Shenoy is your teaching assistant. He is the first author on both of these papers. Do check these papers, okay, where we have given all the details. Now I am not going to spend the time spelling out how we made this, how we made the choice, how we made the board, how we made the connection with the microcontroller. All those details are available in my papers. I request you to please take the time and read, because if I start describing that, then that will become the main focus of this video. So we will stop here. We will continue our discussion in the next video. So in this video, we looked at linear kinematics, angular kinematics, and various ways to record, measure kinematics, and we had a discussion on essentially a comparison between various types of technology that is available to measure. And the take home message is that, it all depends on what you want. Cost is a constraint, the accuracy that you want is a constraint, the specific requirement in terms of whether line of sight is needed or not, line of sight occlusion may happen or not in your task is a constraint. All these things play a role in your decision to go for which measurement system. So we will stop here. We will continue our discussion in a future video. Thank you very much for your attention.